Hello, today we're going to start our work in integration, which is kind of the opposite of differentiation from a mathematical point of view. So what we're going to do is start off by looking at the mechanics of how to do integration, and later on we're going to look at a more physical interpretation of what it gets us. So as differentiation was all about finding rates of change, integration physically is about understanding the area of things. But we're going to come to that physical understanding later. Right now, we're going to look at it from a mechanical point of view because it's basically the inverse or the opposite of differentiation. The rules for integration can be thought about by trying to do the differentiation in reverse. And that's what we're actually going to start off with. We know if we had a function, this is a little bit abstract, but we know how to differentiate this function here. If we have y is equal to x to the power of n, where n is just a number, plus c, where c is just a number, we would multiply by the power and subtract 1 away from the power, and we'd lose that constant. Our constant would just go to 0. So one of the key things about integration, because we're thinking about it as the reverse of differentiation, is we're going to have to figure out a way to find this constant that we've lost in the differentiation, because we're going to be starting from here and getting back to here. That's what integration can be thought of as for a lot of mechanical purposes. So if we start like that, if we start with dy dx is equal to x to the power of n, where n is just a number, how would we use this rule in reverse? Well, coming from y to dy dx, we multiplied by the original power and then subtracted 1 away from the power. So thinking about that as our starting point, and we want to get back here, we'd have to add 1 to this power to get it back to what the power was for when it was y, and then we'd have to divide by that old power, that power of y, to bring us back. So we would add 1 to the power and divide by the new power. And because when we differentiated, we would have lost any constant that was involved in the y, we say that we add back some constant, and we need more information to figure out what that constant is. But it's really important because it's not in your log tables. Well, sorry, there's a little fine print thing at the top of the page that it says constants of integration not written, which isn't very helpful. But the constant of integration is a really important idea. They have explicitly asked questions to prompt you to remember that there's a constant of integration. So it's important that we're clear. This is like undoing our differentiation. And when we went from y to dy dx, we would have lost our constant. So when we are going from dy dx back to y, we have to add back on whatever potential constant there could have been in the original y function. Now, the rules for this are going to come from page 26 in the log tables. Almost every rule that you need is going to be on page 26 in the log tables, and we'll come to the ones that aren't in a little while. But again, to introduce the notation of integration. So I said going from here to here. Well, how do we say that we're going from dy dx to y? If we were going from y to dy dx, we write dy dx. How do we show that we're going from dy dx back to y? Well, we use this symbol that looks like a stretched out S. And the reason it looks like an S is it actually stands for sum. Like I said, we're going to be coming to the physical meaning of integration later on, but for right now, this looks like an S because it is. It stands for the sum of a whole bunch of terms, or an infinite number of terms, physically. And that's why it looks like an S. So this is the integral symbol, a stretched out S. So the integral of dy dx with respect to x is going to be the original function y plus some constant that we might have lost when we did the derivative. So that is our work for now. And these are two of the rules, just to highlight to you again that these are inverses of our differentiation. So we have the integral of x to the power of n dx is x to the power of n plus 1 divided by the new power plus a constant. And a kind of an exception to that rule is the opposite of the natural log derivative that we dealt with before. If we had y was equal to ln of x, then our dy dx was 1 over x. And you can see the reverse is true here. The integral of 1 over x dx is equal to ln of x plus some potential constant. C could be 0, but we need more information to know that. One final note, in our course, there is no product or quotient rule in integration. That's not to say that there isn't an equivalent, but we don't do it in our course. So anytime you are given a complicated function in integration, we are going to have to simplify it down into single terms that we are able to integrate using the rules on page 26, with one slight exception, which is kind of like a reverse chain rule. But anytime we're given functions like this or like this that are kind of a bit of a mess, we have to tidy them down into single terms that we can integrate individually. There's no product or quotient rule that we deal with. So if I'm given something like this, I have a function, we'll say this is dy dx of some function, and I need to integrate it. The first thing I need to do is break it up into individual terms. So I see that I have a common factor of dy dx in both of these things, so I could break them up into separate pieces. I'd have 6x squared all over 2x minus 10x all over 2x dx even, and I can divide that in now, and I get the integral of 3x minus 5 dx. Now let's apply our rule. We have 3x to the power of 1, and we have just a constant here. Now, as we discussed in differentiation, you can think of a constant as having 5x to the power of 0. So you can imagine that there's an x to the power of 0 in here, and you can apply your rule then. So we have add 1 to the power. So we're going to take the integral now, and we're going to have add 1 to the power is going to be 3x to the power of 1 plus 1 is 2, and divide by the new power. And then we are going to integrate the minus 5. So we have minus 5. We are going to add 1 to the power of x. We have x to the power of 0 plus 1 is going to be x to the power of 1, and divide by the new power. And then what do we need to have at the end? Well, this was dy dx. We could have lost a constant in our original function, so we are going to have c in here. So that is our y. If this was dy dx, this would be what y would be equal to. Let's do out another example here. Again, we're just going to use the power rule for the integration. So this one here. So we've got a bracket we need to square out. So square the first by the second and double it. Square the second. And now we have a bunch of separate terms. We can do our integration, add 1 to the power, and divide by the new power. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. And what do we need to include? The constant, because we might have lost it. If this was dy dx, we could have taken the derivative of a constant and lost it from our function. Tidying that up a little bit, we have x cubed all over 3 minus 3x squared plus 9x plus c. And that's our best estimate for y at the moment, because we don't have enough information to find out what the constant could have been. Could have been 0, could have been anything, any number. Now, what happens if we are given enough information to get our value for c, our constant that we've been talking about? Well, we might get a question like this. If dy dx is equal to this, find y if x is equal to a ninth is a root. So if x is equal to ninth is a root, that means that the point 1 over 9, 0 is an element of y. It's on y. it's on the line y. So that gives us a point on the line, which is usually what we need for getting the value of c. So let's take our dy dx, and we know that our dy dx, integral of our dy dx is going to get us back to y plus a constant. 1 all over 2 root x dx. Just like when we're doing differentiation, we don't want to leave our stuff in square root like this. We want to turn this into power notation. So when we rearrange that, the 2 is going to stay underneath here because we don't need to do anything with it. So it's going to be, bring that up on top. It's a power of a half, and bring it up on top. You end up with x to the power of minus a half all over 2 dx. Exactly the same type of step as we would have done in differentiation. And now we have things in power notation. We are able to apply our rule. So we can integrate. And we are going to, this is 3x to the power of 0, so increase the power by 1 and divide by the new power. And then we have minus x to the power of, increase the power by 1, so add 1 to the power, that's going to be x to the power of a half, all over 2 on divide by the new power, plus c. And we end up with 3x minus square root x plus c. And then we're told that this is our value for y. This is our value for y. We've gotten our integral of dy dx, so this gives us y. And then we have, then we want to find out our value for c. So we know that when x is a ninth, y is 0. So 0 is equal to 3 on a ninth minus square root of a ninth plus c. 0 is equal to 3 over 9 is going to be a third. Square root of a ninth would be a third. So in this case, c is equal to 0. So my y function, my original y function I can write down is 3x minus square root of x. And that is how we apply our power rule for integration now. So we can see that it is the opposite, or the anti-differentiation, as our name would suggest. It does the opposite. And if we can get our head around the fact that if we are taking our differentiation rules and using them in reverse, it will give us a certain amount of intuition. And the only other core thing that it often comes up as an issue is we must remember that we could have lost a constant when we were taking our derivative. So we have to add on this constant back onto our functions after we have taken the integral. And that's what we need